All right, can you start? All right, so let us recap on what we have discussed on last this class. We started with module 5, and in that, the basic understanding of it is for the integrity of the message. By that, what we mean is that whenever we are sending a particular message, we are supposed to make sure that the data is definitely confidential, but we haven't looked into the integrity and the authenticity of the data. And that's what we are trying to focus on in this particular module using certain conditions called cryptographic hash function. And in cryptographic hash function, the basic preliminary observation is that we will have a message and that message will first undergo some kind of an encapsulation, and that is what the hash function is doing. And based on that, we are going to generate something called as message digest, which will be nothing but an image kind of a formation of the data or of the message that is being sent. And what the process is that this message digest along with the other encryption, be it a symmetric or an asymmetric, finally it will reach to the destination, and the destination user or the receiver will have a comparison of the message digest that is supposed to come and what he has actually received. Based on the comparison, it will indicate that whether the message has been concealed properly or the authenticity or the integrity of the message is maintained, or if not, then it will be a retransmission that will take place. And in order to do that, we require this hash function to follow certain rules or properties, in which the three basic properties which we come across are the three pre-image, the secondary pre-image, and the collision resistance. In that, the basic idea is, if we don't go to the details of it right now, the basic observation is for any cryptographic hash function which we are going to generate, it should have a principle in which there won't be a situation where there will be two sets of input which will generate the same message digest, which is basically the collision resistance for you. All right, if you remember the diagram, I think the diagram was easy for us to understand. So this was the diagram I told you that it's the collision resistance we are calling it, where there are two different set of input, but it is generating in this particular diagram actually, it is non-resistance diagram. This is kind of a faulty diagram we are talking about, where there are two different input, but the digest is coming as same. This should not happen. This should not happen for any generated hash function. Similarly, the other properties also, the pre-image resistance will be such that for each and every input message, there will be a separate set of hash function which will generate it. So in that case, even if the intruder will have a certain hash function, it is very difficult to retrieve back which particular original image is supposed to generate that hash function. So basically, these properties will make sure the hash function is good or bad. That's the basic rule of it. Now let's discuss about the property or the application of these hash functions, how they are going to utilize. Like already we know a bit from our discussion, but if you see this few schematics of it and how these hash functions are going to be used. For example, the first one, if you see the first diagram that you are observing over here, so we have a message which is lying somewhere here. Okay, now it goes to some kind of an hashing over here, which is capital H, and both of these are appended. This symbol is called as appending. All right. So both of them are appended, and after that appended, whatever the message we are generating, now we are going through an encryption. Whatever we have discussed so far up to module number 5, in fact, or module number 4, in fact, that we were focusing on these areas actually. That we are doing an encryption with certain keys. Now keys, how they are generated, how they are shared, and all those details we have discussed. But now the question is that you can observe here the application of the hash function, that before the encryption happens, we might do a process in which we are making the message to go through an hash function, and naturally there will be a message digest which will be generated over here, and that message digest is used for the encryption, and naturally when you are receiving at the receiver, the message is segregated out, and the hash function is, this is the hash function actually, this hash function is tested and compared whether it is the correct hash function that has been received or not. And naturally we will decide whether it is correct or the retransmission will take place, just like we had done on last day. If you observe over here in this first case, what we are providing is, we are providing the authenticity as well as the confidentiality. That's why I mentioned A plus C. Confidentiality, we are not focusing that much right now. As I said, that is primarily attributed to the encryption techniques and the algorithm that we have discussed, which we are keeping aside for the time being. We are mostly focusing on the integrity and the authenticity of the data. Alright, so in that case, if you observe in this particular case, the message is concealed and in a way we are providing an authenticity. The other second way of doing it, you can see the message plus concatenated hash code is encrypted using symmetric encryption. This is the encryption I'm talking about. Now, if you take the second one, this is another set of arrangement that can be made. And in that, what is happening? The hash function has been made to go through an encryption. The hash function that is generated, that also might go through an encryption. And after that, whatever is generated, that goes through an appendment. Alright, so there are different combinations based on different need. For example, in this particular case, you observe that it is only providing authenticity, but not very important as a confidentiality. Okay, it is providing a very good authenticity, but the confidentiality is not that much, because all throughout, if you observe over here, there is no usage of any key whatsoever. So the data is almost lying like a public data to everyone. Now, just to give an example on this, just to mimic the scenario like this. For example, I am sending you a message over in Teams that today there won't be any class in the afternoon session. Now, as for the user, as all of you user, to you, the data is important because the authenticity of the data is that sir has sent the data and we don't have a class in the afternoon. But do I need to be so confidential about it? The answer is no, we don't need that. Because even if anyone knows it, it doesn't matter to them because they are not part of it. And even if they are part of it, it doesn't matter to them that much because it doesn't contain any important information. Alright, suppose I give you an information over in Teams or in some generic idea that this is the question paper I'm sending you. Now that becomes a confidentiality. That should not be the case. That should not be there for the other batches. For example, for your batch, I have made a paper and I'm sharing it with you only. So that becomes a confidentiality. So in the first case, we don't need the confidentiality. It is generic message. It should be broadcasted to everyone. So in that case, this scenario might be an advantageous one. So depending on how we require the data to be sent, the hash functions and the encryption on top of it might change. So the third point, if you see, the third way of application is to make it a little bit more secure, if you say. Now you observe here, it is possible to use a hash function, but no encryption for message and authenticity. Why? Because the message goes unprotected. We are sending the message just like that, without any encryption, without any hashing, nothing else. This is another set, like third option for that matter. And you can observe there is some kind of a seed value based on which the hash function is generated. And that hash function goes into the appendment and then finally it goes over here. Now the problem over here is again the same thing. The confidentiality is missing over here. The authenticity is there because we are working around with the hash function and we are somehow generating an hash function just to make sure to identify the user who has sent the message or whether the message was sent from a proper source or not. But what the message content, if at all it gets disturbed or not, we are not bothered with that. So that's why you can see the message doesn't have any key whatsoever. So that's again another example where you only require an authenticity, but we don't need a confidentiality. Even you can see the fourth one, that is another set of way in which the authenticity, please sit down, authenticity as well as confidentiality both can be maintained. Now if you see very clearly the same diagram we have, but except you can see there is an encryption going on here. It's very like it's a kind of a practice like based on what we are supposed to give. Suppose this third set of block is essentially is required. We are preferring that to go. So we will do that, but if I want to add a confidentiality on top of it, we will use some kind of an encryption over here. Now for that we might use a DES, we might use an AES, we can use an RSA or whatever the algorithms, encrypted algorithm, what we know. Alright, so that's how the hash function plays its role in different ways the application of it based on how we are trying to get the data at the receiving end. If it is authenticity is what we only require, the encryption might not be that important for that matter. Or for example, if I only require both the authenticity as well as the confidentiality, then different set of arrangements can be made on top of the hash function in order to make it both. Like there are many other configurations as well. So based on how we are trying to design it, it will change. Alright. So now let us discuss about the different ways these hash functions can be generated. Alright. So that's where the discussion comes in. So the cryptographic hash function, as you can see, there are two ways usually. Like mostly the thing is for all the hash function, primary attribute is that whenever we have an infinite length of data, if you say, or a large set of data or bits of data, after the going through the hash function, it will always be of finite length. That is the basic property for any hash function that we come across. Alright, and that can be achieved by something called as iterated hash function. It's a very complex process, I feel, but I'll try to give you as much simplified version of it because it has evolved. In some of the cases, it got isolated in, like, it is completely redundant nowadays. New algorithms, new iterated hash functions are also developed, even lately around 2011 as well. So it is an ever-growing thing. But the basic of it remains the same. The crux of it remains the same. On top of it, we go on changing things. So let's see one by one what are these iterated hash functions. So this is basically a very simple diagram to explain you what exactly is iterated hash function. So if you observe over here, the arbitrary input message will be of m length because we don't have any control on the data which is coming. What we can control is that we can generate some kind of a compression function. This is nothing but the H function. The compression function is nothing but the cryptographic hash function, which will generate some kind of a fixed value over here. Alright, so the point is that irrespective of what the data we are feeding in or the system is being fed with, we are supposed to generate something which is completely only of certain duration, like of 512 bits, maybe of 128 bits, whatever the requirements are for the system. Alright. So in this particular segment, we are going to discuss about this compression function and how it can be developed. Because this got the development started in around 1990. So it's a pretty new thing that compared to all the other theories that we come across. And that's what I tell you, that this compression function is going on changing. Even in 2011, people are designing, or even now 2022, they might have designed some new algorithms on top of it. But where it actually started and where it now, whatever is there in our syllabus and all, that is what we are going to discuss today. So let's discuss the first thing. So this is the first of the significant iterated function block diagram where everything started, and this is called as Merkle-Damgard scheme. If you observe here, few of the important things. First is the original message. You can see over here, the original message we have, it will always have something called as padding. And why it is required? Because if you remember, padding was required to make the data length to be of some finite duration. So if you are supposed to be having a 512, the original message on which you are going to apply the algorithm is of 512 bits, and your original data is of 200 bits. So basically you have to append 312 bits or pad 312 bits in order to make it 512 bits. Alright, so that's why you will find that as we go on, this padding part will play a very significant role. So whatever be the original message, you require some kind of a padding that will take place. After that, we are going to divide that into equal halves of certain number of bits, like n bits over here. Alright, now we are going to divide that into n bits. Now you can observe what we are trying to do. Now we are going to define some function f. This f is actually indicating the compression function. So irrespective of what n bits we have, we are going to generate an h1 which will be having an m bit duration. Am I making sense? So whatever be the number of bits, you are going to divide that into block, and each of those blocks will be fed through a system just like here in the function. Now that function will vary in different cases, which we'll see, and based on that there will be an input over here, like here it is h0, which is an initial hash function value given over here. And based on that, there will be some function, some operation that will go on in this f. And finally, we will generate some kind of an h1. And as the design suggests, this hash function, the first stage hash function, is going to fed as the input to the next. So that's why it is called as iterated hash function. Understood? So that is how the process is. So we are in a process. We get the original value, we pad whatever the required data set we require, how many number of bits we need to add, we do it. After that, we are dividing it into some kind of a bits. This also depends on how in our system, how our algorithm is defined. And after that, we are going through that data through some kind of a function, f, which can be defined in different ways. You can imagine that f can be a kind of an algorithm based on which the final data m bits of hash function will be generated. And this ht that you are seeing at the end, ht at the right hand side, this will be the ht which will be used for the message to get the message digest again next time. So remember the structure. The message is here, then we have a hash function, and finally we are getting some kind of an hm. Right, so that this h is what we are generating over here. Okay, this whole discussion is based on that h. Finally, based on that final h, we are going to append that on the original message, and we kind of encapsulate that, and we will generate some kind of a image of the message, which we have already discussed for message digest. Alright, so you can observe here in this case the very generic function that you can see from this model, that the function will be nothing but hi minus 1 comma mi. Now there can be any operation, it can be a XOR operation, it can be an if operation, it can be an AND operation, whatever it is, a binary operation, whatever you feel like. And based on that, we will generate the next set of hi, and it will go on. Now why this model is important? Because based on this model itself, all the discussion on all the iterated hash functions came into existence. Because if you will soon find that all the algorithms that we are going to discuss, the first set, original message and the block division will remain as it is. Except that this f and the generation of it will change one by one. In different ways. Naturally, in some way there will be some disadvantage. That disadvantage was taken care by the next one. Like that. The second one will have certain disadvantages. The third one will come up with a little improved one. Like what happens in algorithms. So like that. Alright. So keeping that in mind, the two groups in which this compression function belongs to, one is called as the message digest concept, and the other one is called as a secure hash function, or the secure hash algorithm, or SHA. Now SHA is a more recent one. As I said that SHA 512, what I can see from the internet and all, it is around 2007 to 11. That time this algorithm is still evolving, this SHA. Whereas this message digest concept gave rise to SHA. And this is in around 1990. This came in around 1990. There was a famous paper by Ron Rivest where he actually proposed this idea of message digest or message digest based solution for compression function. And this Ron Rivest is nothing but the person who has done the RSA. The RSA stands for R. So that guy, same guy. Alright. So now message digest, what happens is that it had different flavors. Just like we have version 1, version 2 like that. You will have MD4, MD5 like that. MD5 was the last one. But again, as I said, around 1995 and 96 like that, it got obsoleted. But MD5, the process with MD5 came from the idea of MD4, which we are going to study in fact. And this MD5 gave rise to SHA. Understood the flow of it. So that's why we have to understand MD4, bits of MD5 maybe, but then we'll jump to SHA directly. But if I don't go through MD4, you won't be able to understand the SHA for that matter. Because then SHA will be easy to understand. Because it will be repetitive of what we have done for MD4. Correct? So this is what the thing is. And as you can see, secure hash standard we call is SHAs. This is standardized by the NIST. Alright, the standard organization as we call it. So this is the difference of the different variation of SHA. We'll come to that later, but just to give you an understanding on the different set of flavors of it. This is the only one is relevant for us right now. SHA 512. 512 stands for 512 bits that it tries to process at every time. Alright. So if you see over here, so the different specifications as given over here, and everything is much more like it is, like you can see over here, keeping the number of rounds and words almost the same. It is providing with a message digest of 512 bits. Compared to other bits, it is much better. So we'll see that later, we'll see when we come across SHA. And the Whirlpool, which is the other segment of it, message digest is one, SHA is one. The third one is called as a Whirlpool. And in Whirlpool, this is also an iterated cryptographic process, but in that we are using modified AES. AES we had already discussed, so we will find very similarity in this algorithm where the compression function will be working on something, some model, where again the same kind of process will come in, sub-bytes, size orientation, the shifting operation, mixing operations, all those things will come, except that there will be added on features to it. Alright, so this is again one of the ways of doing it. This is also there in our syllabus. So SHA and Whirlpool is what we are going to discuss. Post we are discussing about the MD4. Alright. Now before going to MD4, let's quickly round about, like, brief on whatever the function that we have discussed about. So this is one of the scheme that is available, which is called as Rabin scheme. In that, if you observe, this is the same block diagram that we have discussed in the very first case. But this here, the function is defined over here. And if you observe very carefully, what they have suggested is that when the message block M1, suppose you have M1, the message will be considered as the key. See over here, the message is considered as key. You can see it's mentioned over here. The message block you used as the key. The previously created digest is used as the plain text. Just an algorithm. This is nothing to do with why is to be done. It's just a process that the scheme indicates, that we have a 80 over here, the initial value of the digest, and we will generate P over here. And the ciphertext which we are generating, this is nothing but my next set of hash functions. That will be iterated again next time. So it will go here. Again, the next block set will come over here, which will be acting as a key, and like that, so on and so forth, it will go on. But as you can observe, this is not that secure enough. It is a very generic, easy way of doing it. And you can see that the size of the digest is the size of the data block. So if you are using a DES, the 64-bit digest size is only what you are getting. But it was observed that after a certain period, the 64 digest size can be very easily deciphered, and we can find out what can be the collision resistance is very poor in this particular hash function. So that's why the next scheme that came in, the Davis scheme, in that what we observe is that we are looking at a same scenario, except that there is a feedback going in. You can see over here, there is a feedback going in over here, and there is an extra XOR operation that we are doing, just to make it a little bit more secure, nothing else. But the process is, you can observe these steps are same. These steps are same, except the function, the property of the function is just a bit changed. Alright, naturally you can imagine these are all obsoleted, that's why they are not being used that much. So this is how it is generated, and finally the M bits are generated over here. To make it even more a bit complex, you can observe over here, the orientation changes. It's a dual of actually the first one, Davis scheme. You can see here, the plain text is used as it is. Okay, the plain text is used as it is, but the hash function is used as the key. In the first case, the Davis scheme, it was the opposite. The message was used as the key, and the hash function was used as the message was used as the key, yes, and the hash function was used as plain text. Here it is just the opposite. And also on top of it, the feedback from the previous scheme is also intact. Just another algorithm that they have defined. Each of them has a certain amount of disadvantage in terms of the generated word length, like the digest scheme. Okay, so that's why it is not used anymore. But this is how it iterated from one to another. Last but not the least is the Mugachi-Prenil scheme, and this is a very important one because the Whirlpool scheme that I was talking about actually deals with this particular arrangement. In this, what happens, you can see that a message which is coming over here, this also takes part in the XORing operation. Unlike to only the ciphertext and the hash, over here you can see there is a link which is coming in from the message itself. So three element are getting XORed once again. The message, the ciphertext, as well as the hash function together. So that makes it a little bit different and more secure. And as you can see, used for Whirlpool hash scheme, which we will discuss at the end of our discussion. So this is some of the hash function or the basic building blocks to hash function generation. But mostly this all had, like the previous one, this is far better in fact. gave rise to the concept of MD4 or the message digest based hash function, iterated hash function. And for that, you can see this is the generic structure that I was talking about. So if we observe that there are MD4 is what Rivest first introduced in 1990. So based on that, you can see 1995 it was the SHA1, and you can see 512 is around 24 that it got standardized. Even in, as I said, in 2011 also some modifications have come in for SHA. But that's the branch, and that's why we are going to start with something called as MD4, because that's the basis and the basic algorithm apart from the what we have discussed so far, and the most critical in discussing SHA and particularly MD5. Alright, so now let's see about the MD4 hash function. Now this is where I want you all of you to focus a bit, because this becomes a little complex, I feel, while we are discussing over here, because it's a little difficult, but I will try to give you a block diagram which is not there in your books for that matter. So please follow that carefully. Now what over here happens is, this is also, as I said, MD4 family hash function are all based on Merkle-Damgard scheme. That is the first one. The same thing, that you are having an original message. The original message has some padding also. Let that be of some duration, some bits. Then it is divided into different blocks. And those blocks are going to alter with certain amount of words. Here the extent of the understanding is with respect to words. If you see here, these are called as words. A, B, C, D are the initial registers for the hash function. This A, B, C, D is nothing but, if I call it as 80. Please focus on this, concentrate on this very carefully. 80 is what? 80 is the initial hash function. If you remember in the previous examples, 80 was here, the initial hash function. So this ABCD is the representation of that 80, which is nothing but a 32-bit register. And like in many of the AES algorithms, and we have already observed that we will have some predefined table for the initial approximation. So here, this particular arrangement that you are looking at is the initial approximation of the words. For that matter, for example, 67EF like this, if you say this way, if I block it this way, so the content of ABCD will be something like 0189FE76, like that. So ABCD will be of that element. And it will go on with different changes and ranges. We'll see that later. But that's basically an ABCD is a register which will have the initial content like this. Alright, at step 1, maybe the first elements will come, the first 4 columns will come, then the next 4 columns will come, third will come, because it's an iterative process. So it should be updated once in a while. So that updation will happen over here. But whatever it is, this is the 80, the initial hash function. Okay. Now, if you observe this diagram, I'll come back to this diagram later for a particular reason, because it might confuse you at this point of time. But just in general discussion I'm talking about, you can see that what is exactly happening. Now, we are seeing a scenario where there is some kind of a function which goes in over here, f. This is not the compression function, this capital F that you are looking at. Okay? This will be defined by some way. So, for each and every round, we will have certain function that will be based on the inputs which are coming in from B, C and D. See, observe this carefully. I'll give you another separate diagram to understand this. So, we have 3 of this B, C, D. If you see the inputs over here. So, B, C, D will act on this function. The generated output will have some kind of a zoring that will take place with the 32-bit over here of A. The message will come over here, which also will be a 32-bit, based on which there will be a new state matrix that will be generated. This Ki will be a constant matrix. Just like, you remember in case of AES, we had done like rot function or rot word, we had certain template, right? Similarly, this Ki will have certain templates. And further, this will be a left shift operation. Whatever it is, don't get panicked like why it is happening. But this operation, 3 XORs will happen And finally, there will be a left shift operation. And after that, there will be a change if you see the orientation of the bits. So the D bits comes to A, B is updated by this one, but directly B comes into C and C comes to D. So this ABCD, you can say this is A prime, B prime, C prime, D prime. This will be the next hash function to the next round. I know it's a little confusing. I'll give you one by one what we are supposed to do, but let me just go through the part of it, then I'll come back to the diagrams. All right. So first we have the initial word and we will go on doing this process. So let's see about the description of it. So first of all, one 512-bit input message block is denoted by MI. So as I said, this is a 512-bit that we are going to have for it, but the message digest will be of 128-bit. The original message will be of 512-bit length. If it is not 512-bit length, then definitely if the original message is smaller, then you have to pad and to make it 512. But that 512, why? Because we have to divide that equally. How we are going to divide? We are going to divide that using each block of 32 bits. Right? We have to divide that by 32 bits, each of them. So, and each of these 32 words, as I said, the 32-bit register word, this is my ABCD. Already in the previous diagram it was mentioned. So these 32 words are denoted by something of AIJ. As you can see, it's mentioned over here. I have mentioned it in terms of ABCD, but they are mentioned as AI, minus 3, AI minus 1 and AI minus 2. This is the nomenclature used in the books, but I tend to feel that this is a bit confusing to understand at times. So that's why I kept it general as ABCD. Alright, so the point is, we have a 512 bits of data. We are going to divide that into 32-bit block set. And each of those block sets will undergo certain function. Remember, don't like visualize that how the function is working. So there is a function in which the inputs are these 32 bits. Each of these function will undergo certain rounds. So let's see one by one what are the things. Alright, so before going to this, let me draw the diagram and let you understand this a bit up to what we have discussed. Alright. So just follow this carefully, what we are trying to do. So we are in a process of something like this. We have, this is my 512 bits. Suppose this is my M1. This is another 512, which is my M2. Like that. This is my MT. This is what is mentioned over here as well. 512-bit input message of block is denoted by MT. So this is what my denoted is. So we go back. So this is my M1 block, right? Now, suppose we focus on any one of this block. The process is, let me go through the process first. There should be a 3 set of replica of the same data. If I say this is M2, M2, M2. So this M2 I'm looking at. Alright, there are 3 set of replica. Why we need 3? Because each of these 3 replica of data will undergo 16 rounds of combination. That means total 48 state it will go through. I'll repeating once again. 512 bits is what the original message is. That message is, if you say M2 we are focusing on, that M2 will undergo 3 sets of rounds. Like 3 sets of rounds in a means, like each round will have 16 states. So this is 16 state, this is 16 state, this is 16 state. So like that 3 times it will go. So around 48 times, 48 changes it will undergo. Alright. But as I said that it is repetitive process, so let me just focus on any one. So suppose what I mean is that this will be something like this. Small m0, m1, up to M15. Similarly, this one also will have M0 to M15. Similarly, this will also have M0, M15. Now, this M0 to M15, these are nothing but the words, 32-bit words. These words will go through that process of XORing that I told you in the first diagram, all right, based on the specific function for that particular round. See the complexity, how it will come in. So this all 16, if I combine it this way, this will go through, I'm just directly drawing this way. This is divided into 3 rounds, round 1, round 2 and round 3. So we are in a position where we are having the 32-bit or the words we have generated, 3 times we are repeating it. So total around 48 we have steps that we have to come across. And that what I mean is that we will have this is called as S0, state S1, like this it will go on up to S15. This will be my S16. This round 16 will go to S31. This will be S32 and it will end at S47. So each of this, so see, this all starts from M2. So one 512-bit block of data actually goes through these 3 rounds of permutations. And each of this round, after each of this round, there will be one hash function which will be generated based on that ABCD configuration that I told you. So that ABCD is fed with this round. It goes through this all the 16 to 31, that is 16 steps. Again it will go here. So in between here there will be another ABCD which will be generated. Finally after this will be H of 3. So that H of 3 will be used for the next set of M4 of the bit. Here, can anyone tell me what will be the input here? What will be the input here? This one, the top one? Here. This will be the input. What will be the input here? H1. H1 is what? The output of the M1 block. M1 will also have certain like this. So the output of the M1 set will have H1 as the message digest or the hash function. That hash function will be used to start the procedures for this. What will be H1? H1 will again be some combination of ABCD, where ABCD all are 32-bit words. So what I mean is that this state is something like linked like this, M0, M1, like that. Like M0 word is associated with one state. M1 word is associated with second one state, like that. So 15 odd over here, 15 words are there. So you have 15 state over here. Here also 15 is there. So we have 15 or 16, whatever you call say. So that 16 are here. And then the next 16 is over here. Am I making sense how we are doing it? So for each block, it is divided into 3 different regions and each of them are doing in this way. And interestingly, or rather to make it even more complex, each of this round will have different set of binary operations. So that means that is for round 1, it will be an if function, if x, y, z. For round 2 data, it will be a major operation, major x, y, z. They are defined by some normal binary operations. And this will be an XOR of x, y, z. Where is this XOR and all? If I go back, this function is my if, when it is in round 1, this function is my majority, x, y, z. Remember, x, y, z, 3 input. And if it is in the round 3, this should be an XOR. So this diagram, why I told you that this is not the initial stage, this is ideally indicating S of k, if you say. For every state, this operation will take place. What is every state? This state. This is my state 0. S0 is state 0. S1 is state 1. So for each and every state, like for 15 states, it will undergo this operation of function, XORing with 3 input, then XORing with the message bit. This is my M0. This is my M0. So M0, suppose the message comes in 32-bit, ABCD is generated, that goes in with the function. For if it is round 1, it should be an if, otherwise it should be a majority, we call it MAJ, and then we have XOR otherwise. So that is being mentioned over here in this particular diagram. Alright, so we observe that for this round, now if you see the diagram that I have drawn over there, 0 to 15 if state. So this if, main and XOR, these functions are the intermediate function which is used at each state. And for each state, there will be a generated ABCD. That ABCD acts as the input to the next state, and so on and so forth. And this goes on for 48 rounds. So remember, this is what this 48 rounds we are designing for 512 bits. Now imagine for all the other 512 bits, whatever we have, the same kind of operation will take place. So ideally, this diagram, if I go back to this diagram, this one, suppose this empty. So for empty also, similar kind of operation will take place. And whatever we are getting out of that empty, the final message block, that will be your message digest. That is the principle we are going to adopt for MD4. How difficult it is? Yeah, please. What will be? H3. H3 is because we are considering M2. Oh, acha, yeah, that should be H2. Correct. H2. It should be H2. Correct. So in that way, it will go on. Right, and that, as I said already, that they are the standard values should be there. So if you observe, sorry. So we have this as the binary operation, as I said. Input message also are standard, as I said, 512 bits should be there as always. All right. So this is basically the structure of it, but I am not focusing on that much because when we discuss on SHA 512, I will give you a proper example of how these input bits are made. Basically, remember for the time being that over here, for all these algorithms, we are trying to make initial block to be of same duration. So if it is of, suppose the input original message is of 200 bits, we have to append 0 padding to make it 512. For example, you can see over here, and the padding is very simple also. What padding is that, suppose you have to add 300 bits as padding. So it will be 1, the first bit will be 1, and the rest 299 bits will be all zeros. Up to 299. Just an example I'm giving you. Because I have to make it 512. Okay. So for that, suppose 200 bit is the original message. So we are left with 312 message. That will be a padded bit. Now padding is very simple. What we are going to do, for 300 bit, the first bit will be 1 and the rest 299 bits will be all zeros. Simple as that. So that is being shown over here, but the true example becomes much clearer when we discuss about SHA. So we'll come back to that later when we discuss on SHA. But let me just give you the briefing of a little bit before we end on. So if major and XOR operation is now fine, This is the second operation, the one that we were discussing as Ki. Do you remember this diagram? This Ki. This Ki is a standard template, standard matrix or state, if you say. And that is given by a particular state arrangement is something like this. So when you are in 32 to 47. So when you are in 0 to 15 rounds, with the each function working on as an f, the constant matrix will be all zero matrix. Same way, when you are in 60 to 31 range, round 2, you are in with the matrix function, your function as energy xyz. This will be my hexadecimal notation. This is again standard. And same as the last one. So each and every time when you are in particular round, you have a specific Boolean function, you have a specific Ki, along with a different set of M which is coming in one after the other. So that is, you can see over here, you can also see over here, 3 rounds of having 16 step each. So that makes it 48. That's the diagram I was drawing. Alright. Finally, the answer to all this is the calculation part. Please make a note of this equation only. So AI is given by, AI is the updation, like how ABCD is updated. Very simple in fact. So this is my AI minus 4. This is given over here, but if it is not visible, that's why I've given here. AI minus 4, XOR, Fi. This is the function. This Fi can be a if function or a XOR function or a match function based on which round we are in. For that, the inputs are AI minus 1, AI minus 2 and A minus 3, which we had discussed as X, Y and Z. Or BCD, you call it in that row. So that function is coming in. The message is coming in also. And the constant Ci is also coming in over here. Am I making sense? See remember the diagram, first diagram. A was coming in, message was coming in, the function block was coming in, the output of the function was coming in, and finally the Ci was getting connected. So this is what we are going in. This is my A, the function part, the output of the function, the message, and the constant Ci. For that particular round. See, I is here, I varies between 0 to 47. So which step you are in? If it is 15 step or suppose it is in 17 step, that means you are in round 2. So your function will be a merge. Got it? So based on that, the calculation will happen and that updation will come in AI. And based on that, you can see the words are going to represent it in this way. Again, a standard procedure that is to be followed. Forget about it that for the time being. And finally, we come across a scenario where the MD4 hash function is used. You can see over here the final outcome. As I said, the A is actually going to D, B is going to C. All right, that arrangement that I am talking about. So this one I am talking about. A is coming to B, B is coming to C, C is coming to D, and D is coming to A. So that is being mentioned over here. You can look at it later. See here. Original ABCD and this is the updated ABCD. Whatever we are getting, that is my new ABCD. And that is happening for each and every steps. Right? Not only that, there is another one that we missed out and that's where we will end our discussion. And that is this SI. What is this SI? This is nothing but a left shift operation. Nothing but a left shift operation. But that shift operation is also standardized. Just like remember in case of our DES, most probably it was there that which round we are in, based on that 1 bit or 2 bits were getting appended, right? Remember the process. Same with here. Here what happens, you can see here, if it is between 0 to 15, this is the nature. You can see that there is a repetition. 3, 7, 11, 19. So it's like which state you are in. Suppose you are at state 0. You are at state 0. Then left shift by 3 bits. If you are at state 1, left shift by 7 bits. If you are at state 2, left shift by 11 bits. If you are at state 4, depth shift by 19 bits. If you are at state 5, 3 bits. Understood the process? It's like repeating the process. So up to 15, you can see total 16 odd state we have. So 0 to 4, a certain amount of shifting. 5 to 9, it will be 5 to 9, 5, 6, 7, 8, 5 to 6, 8. That will be another set of shifting. Then 9 to 12, another set of shifting. 13 to 16, another set of shifting. So this is what we are looking at. You can see for all the cases, it is repeating. Right? So that's amount of repetition, this left shifting that is happening, that is also dependent on which state you are in. And that goes for every round. So for 48 total state, you have to go on doing the same process again and again. Alright, so that is about the MD4 process. Most of the time, we will try to make sure the process needs to be explained in your answers. Very rarely we'll have come across any numerical as such, because as you can see, the extent of calculations is pretty difficult at times. But why I'm mentioning, even you will find that in the latest of the books for the Farouzen and all, they have in fact excluded the MD4 from the discussion. They directly go to SH 512. But the point is, in SH 512, if you are not able to understand this, you won't be able to explain, understand that part quite an extent, because this is the origin of it. So the logic is, if I go back to the diagram where we end our discussion, so we have a 512, just to recap on what we've done, we have a 512 data, original data, which is 3 times replicated into 32 bit or 512 bits first of all, and those individual 512 are divided into 32 bit each, like 16 odd data bits. So that's why M0 to M15. Now, each of those bulk of M0 to 15 words are subjected to round 1, round 2, round 3. And each of those rounds are going through which each individual function. For round 1, it is the if function. For round 2 data set, it is for the majority function. And the round 3 is for XOR function. All this is what we are trying to do. We are trying to update the ABCD, which are nothing but the register, which are going on updating itself. And each and every round output is fed to the next round input, and as on up to it goes on until the 47th round. And finally, whatever we are getting at the output is the hash function for that particular round, after that particular round. So like that, we will go till the Tth round, and finally we will achieve the final hash function that needs to be added to the message to create the message calls. Right? I know it is a bit difficult, but when I upload this whole document and all, I think it will be much easier for you to understand. And many of them are standardized. So maybe we will touch upon next day before we start off with SHA. Okay? So that it is a recap that we can do later on. Okay? Alright. Thank you.